going on, Linear Algebra Bros? It's Mr. C here, and in this video we are going to demonstrate that a set of objects is not a vector space. In particular, let B be the set of all pairs of real numbers of the form x comma y, so order two tuples, and it looks like there's a condition on x. X needs to be greater than or equal to 0. In other words, there can be no negative x values for such an ordered pair. Now, we are to assume the standard operations on R2, and what that means is when we go to add vectors or sets of real numbers of this form, they're kind of one and the same in this context. We add corresponding components, and to scalar multiply these objects, we distribute the scalar into the components. It says here, show that axiom 6 fails, which would therefore imply that this set of objects is not a vector space. So I think it might be helpful to draw this set of objects out, or at least get an idea of what the set looks like. So certain objects that would be in this set would be, ordered pairs such as 0, 0. That would work since the x-coordinate is greater than or equal to 0. So that would be an element of the set B. So with something like 1, 1, but something like negative 2, 0 would not be in the set B. And the reason for that is because the x value is not greater than or equal to 0. Now, if you write out more ordered pairs, you kind of get a sense of where these objects reside, specifically in the coordinate plane. All of these objects would lie along the y-axis and to the right of it. So essentially, these objects come from quadrants 1 and quadrant 4, as well as the positive y-axis and negative y-axis. So this right here represents the set B. Now, axiom 6 says that for all scalars k and all objects from the set B in this case, let's say an object u, ku has to be an element of B for any scalar k. Now keep in mind, k comes from the set of real numbers. Now check this out. Let's say I choose the point 1, 1. Okay, so 1, 1. That's certainly in the set B. And let me connect it to the origin to form a vector. Alright, so 1, 1 would be the components, hence the component form of this object. Would there be a scalar that I could multiply 1, 1 by in order to take it out of the set B? And the answer to that is a resounding yes. In fact, there are many scalars that we could multiply to this object, which let me call this u. In fact, any scalar that's less than 0 is going to take this vector outside of these two quadrants of the coordinate plane. So what does that all mean? Well, I'm going to say let k, and I'm just going to pick one negative value. Let's say let k equal negative 1. Then ku would equal negative 1 times 1, 1. And remember, we're assuming the usual or the standard operations on R2. So the operation of scalar multiplication, which we have set up here, would tell me to distribute the negative 1 into the components here. So we'd have negative 1, negative 1. And if I go to plot that, that takes me outside of the set B. So ku would not be an element of the set B. Therefore, well, my therefore would be that. So therefore, KU is not an element of the set B, which means that axiom 6 fails, ultimately meaning that B is not a vector space. So what we could say about this set B is it's at least not closed under scalar multiplication, because we can come up with many more examples in addition to -1 for which k times u takes you outside of the set B. And we don't even have to be, pick that particular vector u. As long as you're, in the set B, using any negative scalar is going to change the first component into a negative number, therefore taking you outside of the set B. So for instance, I might have 1, -1 as a vector v, and if I multiply v by -1, that's going to take me into quadrant 2, because we would have -1 comma +1 upon scalar multiplication, and that's what kv would look like. And obviously that's not in the set B either. So there are many sample vectors from the set B and many sample k values for which we can take ourselves outside of the set B. Alright, and that's where I'll end it. Of course, if you have any questions, feel free to let me know. Otherwise, thanks for watching, and be cool. I'll see you next time, Linear Algebros.